All right, so guys, augmented matrix. So here we go again with something that sounds more complicated than what it really is. So, well, it's too late. I already started.
What's up? What's up?
Oh my God! Yeah.
I'm embarrassed for you now. Yeah. Okay, so back to this though. An augmented matrix. Augmented matrix. Again, the term augmented. It's just not a term that we use very often. You've probably heard the word before, but it's not something that is used on an everyday basis or anything like that. So I know that there are some that may be, I don't know, scared off by using words all of a sudden that are not super common. But let's try to stay away from that. When we talk about an augmented matrix, again, by definition, you can read through it. It says that it's a matrix derived from a system of linear equations, each written in standard form with the constant terms on the right. Okay, so here's big picture. This is where we're going. We're going towards solving a problem that looks like this. Obviously, this is a system of equations. This literally could have been a question on yesterday's test, right? Yesterday's Chapter 7 test, this would have fit. Not with these directions, of course, but if it just said solve the system, okay? We could have gone there, solving the system, getting to the secondary system, after eliminating one of the variables, solve the secondary system, plug back in, we end up with all three variables. You've done this multiple times. So what we're going to try to do is solve this using matrices. So what does that mean? Well, we need to create an augmented matrix. So the whole idea of being augmented is that we're going to really just squish two matrices together. So could we look at this whole thing and pull out the coefficients? Yeah. So before I go any further with that, again, I don't know if it's quite an analogy or what, but we all remember polynomial long division, right? So if we had something like 5x to the fourth minus 7x cubed plus 10x squared minus x plus 6, and I'm dividing this by x minus 3. We could do this. We all love polynomial long division, I'm sure. But I would assume that just by writing up that divisor of x minus 3, a lot of us were like, ooh, now we can do what? Synthetic division. I think that we all would prefer to work synthetic division here, correct? Now, how do I get the rest of this? So it's going to be 5, negative 7, 10, negative 1, 6. Now, why is it that we prefer to do synthetic division? And let's try to stay away from just saying that it's easier, because I agree with that. But why? Why is it simpler though? Go on that a little bit further, Lucy. Yeah. So we don't have to look at the variables. We don't have to look at the x's and the exponents. We just were able to simplify it and look at the numbers. I don't know about anybody else, but I take great comfort in just having to look at the numbers. That's what we're doing with matrices as well. Okay. We've got all these variables. Here we don't have to worry about exponents, but we have to worry about x's, y's, and z's. Wouldn't it be nice if we could look in here and just take out the extra stuff and just focus on the coefficients? So here, that first line, my coefficients are 1, 1, 2, and 3. 1, 1, 2, and 3. My second equation, 3, 4, 4, 9. My third equation, we have 5, 2, 15, 13. Now, we need to show separation between the variables and the constants. So we're going to put a vertical dotted line. Basically, it's just where the equal signs are. Okay? This that we just created, that's what we call an augmented matrix. Okay, now why do we call it augmented? Well, remember what I said augmented was about. We're literally pushing two matrices together. Could we have created a matrix out of these variables? Sure. It'd be this part over here, wouldn't it? Could we have created a matrix out of these constants? Yeah. It'd be that part over there. And when we put this together, we're augmenting the matrix. Okay? Now, again, what did we say about this in red? We said, could we create a system out of the variables? And over here, we said, could we create a system on the right out of the constants? And that's actually what we call them. This is, on the left, if we created a matrix, that 3 by 3, it's called the variable matrix. Or the coefficient matrix. Okay? On the right, we would call that the constant matrix. All right, so that's where we're going. That's, like I said, that'll be tomorrow where we're at. But again, some of the terminology defining that right now. Okay? Again, the augmented matrix, it's going to be the matrix derived from a system of linear equations. All right, now the next thing that we need to draw your attention to here is that each has to be written in standard form with constant terms on the right. At this stage, this shouldn't be a big deal because have we required that you're always putting your constraints, your system, they always had to be in standard form, right? So we hopefully are at the point now to where if you saw a system that was not in standard form, that would look weird to you, okay? So if it wasn't in standard form, you got to put it in standard form. Because if we're not in standard form, then that would be like trying to set up the synthetic division if all of your variables were out of order. If you had like x cubed plus 3x to the fourth minus x squared, yeah, you'd rearrange them in the correct order. Okay? Otherwise, we'd expect everything to get all screwed up. All right? So here we go with another example. We have this system with 3 equations, 3 variables. So a couple things we want to draw your attention to. That first line, my coefficients are 1, -4, 3, 5. Second equation, we have -1, 3, -1, -3. Third equation, let's be heads up here. We have 2. There is nothing there for y. Can I just leave that blank in a system? Is that okay to leave blank in a system? Sure. Can't do that in a matrix. It's just like synthetic division. We couldn't leave a blank in synthetic division. We had to fill with the 0. Same thing in the matrix. So then now we have -4 and 6 augmenting. So again, we're putting that vertical dotted line. So if we were looking at the variables here, again, we call that the coefficient matrix. We'll define it here in a couple minutes. Tomorrow. That's going to be what we refer to as the constant. A couple minutes tomorrow, yeah. It'll only take a couple minutes, but yeah. All right, so a couple things to note here. The vertical dots, they're going to separate the coefficients from the constants. Okay? What's probably going to be easier, especially at this point, you're going to put the vertical dotted line through the equal signs. Like that. That's where they're at. Also, we have to use 0 if a variable is missing. All right, so example number 2, what I'd like for you guys to do here real quick, should only take 15 seconds or so. Please write an augmented matrix. I'm not asking you to solve it or anything. We just want to write the augmented matrix, please. So we have a system. Let's write this as an augmented matrix. Go ahead and do that now, please. All right, Katie, could you give me that first row, please? 5, 9, -1, 8. Perfect. Jennifer, second row, please. And then -6. Good. Ian, how about row 3, please?
7, 12, 7.
Perfect. All right, so guys, if you have questions on your homework assignment tonight that are asking you they're asking you questions about the order, you can do those. If it's asking you to create augmented matrices, you can do those. Okay? Now, beyond that, I know that we are very pinched on time, but I'd at least like to talk about this very, very briefly. Row echelon form. If you've got a good memory, that should ring a bell. We talked about row echelon form very briefly in Chapter 7. In fact, I prefaced it by saying this isn't going to be a big deal until Chapter 8. Okay? But that was the stair-step function. Okay? The system that had the stair-step like this. Remember? Okay? It was number 3 on your test that you took yesterday. And we had one like that to where there were no x and y variables. It just said z equals whatever it was, right? So if you were to create a matrix, an augmented matrix, based on that row echelon form that we've already talked about, this is what it's going to look like. So your giveaways are that you have positive 1s on what we call the diagonal, and then you have 0s everywhere underneath. That's what we refer to as row echelon form. Do we understand that if you can get into row echelon form, we can solve the system? Just like you did on number 3 of the test yesterday. Now, if we understand that we're not given row echelon form very often, how do we get to row echelon form? That's when we're going to bring in those row operations that we don't have time to talk about today. That's going to be a tomorrow thing. We also are going to be targeting what we call reduced row echelon form. Mouthful, yes, but reduced row echelon form, that's if we have an augmented matrix, and we have 1s on the diagonal, zeros underneath, and zeros above. That's going to lead to our answers. Because remember what this represents, that top line. Isn't this saying 1x plus 0y plus 0z? So this is just saying x is whatever that number is. Y is whatever that number is. Z is whatever that number is. So if you can get into reduced row echelon form, you've solved the system. You've solved the matrix. Does that make sense? And that's the whole goal. That's what we're trying to pull off. Now, probably sounds the way that I just explained that, like, oh, it's no big deal. Just get into that form. That's what's going to be the challenge. That's going to be, all right, here's where I'm starting. How do I get these elements in the correct position? And it's a big, giant puzzle. But I like puzzles, and that's probably why I like matrices. So again, tomorrow we're going in with these elementary row operations. Have a great night.